joining. Hello, everyone, and thank you for joining the event today. We are presenting on the role of refrigerants in reducing carbon emission today, and we have people from presenters and panelists from Trane, WSP, and Elara Engineering Group. This event is hosted by CLF Chicago chapter. CLF Carbon Leadership Forum is a global initiative to reduce carbon emission in the building industry. And also, I thank Illinois Green for helping us to host these events. So this is the agenda for today. We have a presentation from Steve with Trane on the recent developments and the conversation on why carbon emission in the building industry and refrigerants is important, and we have to think about that. And we will continue with the panel conversation uh, for about 40 minutes to discuss the next step, the challenges and the barriers that we are facing to reduce the carbon emission in the refrigerants and the different refrigerants types. And then at the end, we will have about 10 minutes at minimum to have you all turn on your camera and unmute yourself and ask your questions and just like simply join the panel. So this is just Steve gonna just like elaborate more on the refrigerants, but I have a couple of really quick slides in the beginning about where this has started. I mean, the conversation about refrigerants started with the Montreal Protocol back in '87 on making sure that the ozone layer is important, and there been some escalation on the with the problems that you have had with the ozone layer. So we had a goal of having CFC free refrigerants by 1995, and that's been achieved. And then we had a goal of HFC by 2030, which been targeted by 2030. And the chart shows us what been the progress of the ozone layer and with the ozone layer since we have implemented the Montreal Protocol. The conversation today is kind of discuss how where we are with this progress and how we can look into the global warming impact of refrigerants other than the ozone part. And I have one slide about the LEED and how LEED help us transform the market for the most part, other than the other standards and requirement that we had in the market. And the reason I have it, because one of the things that we're going to discuss later in the panel is the market drivers. And we had a limited market drivers considering within the certification frameworks like LEED. LEED had a prerequisite and a credit to kind of like push to transform the market to use a better and more efficient and lower ozone depletion and lower global warming potential refrigerants. The fact is, what we're going to discuss today, for the most part, is not covered in a certification like LEED or other standards. We have whole building LCA in the LEED now, but that doesn't include the carbon emission, the operational carbon emission, and the embodied carbon emission from the refrigerant. So that's something that we're going to discuss later. But LEED been pretty helpful to kind of having at least one prerequisite and one credit related to refrigerants to at least push the design teams and the engineers and the clients to think about that. I have one is a slide to talk about why the refrigerants, the impact of the carbon emission within the refrigerants is important when we look into that in the big picture. So if you look at this slide, this is what we did for a competition, and we won the competition, and forever we're going to be proud of that. It was part of the lowdown showdown competition in ASHRAE. And what we did there was like, in addition to the carbon emission that comes from the operation of the building and is associated with the with the energy, we looked into the structure, and also we looked into the refrigerants. And what you see here as this is the conventional build, that what's going to be the carbon emission associated with the refrigerant use. And you see is still not as big as operational energy or a structure, but is the third biggest pie in the chart that comes from the refrigerants. And through our design, we've been able to minimize that with the use of efficient or low global warming impact refrigerant called HFO-1234ZE. So this is why we are discussing that, because in our industry, and the good thing is today, I mean, everyone in the call is a technical person and we don't need to go through the basics. We've been talking about the carbon emission that come from operational energy for a long time. We have started to do whole building LCA and looking into the embodied carbon emission for a time now. But this is the part that we have to start looking into that and including our projects to make sure that we are looking into the carbon emission that comes from refrigerants in addition to the rest. Before we switch to Steve's presentation, I wanted to refer to the event that CLF Austin chapter hosted last month. It was a great presentation. They had the event on the embodied carbon and the operational carbon that comes from the MEP system and refrigerants. It was a broader and a more comprehensive event. And this event, I would consider that as a detailed conversation and as a follow-up conversation to what they had. If you had the time, just we're gonna send the link to that webinar in the chat box here. If you have time, please go and watch that. One benefit about the CLF is there are tons of resources. If you go to the website, there are tons of resources in addition to the webinars like these that are going to be recorded and going to be available there. There are tons of resources related to carbon emission and embodied carbon there that you can all use. So with that, we will switch to Steve with Trane to do his presentation.
Yes, hello everybody. I'm Steve Kwiak. I'm the Director of Next Gen Refrigerant Research. And Mohammed, can you hear me okay? Before I go too far?
That's perfect. I was just muting myself. You're
okay, all right. I've done these presentations before over the web and I spend 5 minutes and everybody's going, we can't hear you. So just want to make sure before we start a little bit. So thank you for inviting me to talk to the Carbon Leadership Forum about refrigerants. Somebody asked me the other day, why do you know so much about refrigerants? Well, I get paid to do it, one, and I eat, live, and sleep it every day for the last 12 years. And starting out with my career 29 years ago, I was just an experimentalist around refrigerants at the last transition. So it's something I love to do and love to talk about. So thank you for inviting me. Next slide. So, what is the, if you're looking at carbon emissions or carbon equivalent emissions where refrigerants fall, in direct emissions, how does it contribute? So, in the last few years or so, I've written a couple papers with others studying, life cycle climate performance on the left of refrigerated transport. So if you look at, this is a system, to haul food around, and even there where we're using a very high GWP refrigerant, 404A, with a GWP around 4,000, and these systems are direct drive systems. So you have an open shaft, so refrigerant leaks are a little higher, emissions are a little higher. You can see even with a 4,000 GWP and a higher leak rate, the emissions from the fuel consumption, which is diesel in this case. I mean, this industry is moving to electrification and battery powered stuff. But if you look at this today, emissions of refrigerants, look at, more than cream on top of the pile. So kind of a breakdown looking at all the different emissions, where they occur in their life cycle, from the manufacturing of the refrigerant to how you handle it, obviously in use, which is the direct emissions, and then the emission equipment manufacturing and installation. So then when you look at this a little more detailed, right? So I focus a lot of time on, the GWP of the refrigerant is this, and we need to get it down. So now here I look at it from a building standpoint. And so we did a paper using the energy analysis model from DOE, and I had some people help me with this. So we're looking at various buildings and various climate zones within California, and these are 410A installations. And what we had compared it to is to a new refrigerant that was emergent at the time, which was what I would call a design compatible refrigerant, 452B. Now this refrigerant is flammable, but we could model, dropping it into a 410A system and get the right comparison very easily without having to redesign the equipment. So as you look here, you can see a little bit of green on top is the refrigerant's lifetime emissions. So, how much refrigerant's in the equipment, and then assumed leak rate, and then, recovery rate at the end of the life. And so you can see that, the refrigerant is a small part of the emissions, but it's easily the one that's easier to control because it's a direct emission. So now you look at the building use, you can see the HVAC load, and then you can see the rest of the load in the buildings, which are, by far the indirect emissions, by far the largest things. So, each refrigerant and how it's applied has different use. I saw that slide earlier where you had the cream competition. Obviously, it said VRF, so that must have been 410A. Then Mohammed mentioned ZE, so ZE has a GWP of less than 1 or less than 10, if you want to call it that, for scatter. And and how you apply it will get you to the lowest emissions possible. So you could have a GWP of 1, right? And then you can emit quite a bit, but you really don't contribute. But you have a GWP 100, and if you emit a lot, it can be more significant. But the goal of the future of refrigerants to phase down the global warming potential of refrigerants as we develop technology that's viable. Next slide, please. So, barriers to adoption of lower GWP refrigerants. So one of the things we do, and I'm the chair of Standard 34, which puts the R in refrigerants. So we have a safety classification, and in the past, it was very easy. Refrigerants only came in as class A1s, essentially, non-flammable, lower toxicity. So when you go to the building codes, you go to the standards like standard 15 or the product codes, they didn't allow, or it was severely restricted on how you use a flammable refrigerant. So it was a no-brainer. If you have a non-flammable refrigerant with a GWP of 1, you can easily adopt that today because everything is aligned within the product standards to the application standard, which is like standard 15 from ASHRAE, to the building codes within the state, or even in building codes in the local municipality, right? So, I mean, they even are different there. So as we look at flammability, there was a big void there that the industry was learning from. So people are really familiar with barbecue grills and using propane or natural gas in your house, and that's one thing. But there's a continuum of flammability from lower flammable refrigerants to higher flammable refrigerants like propane. And the one thing you have to get a takeaway from is flammable is flammable, meaning if you have an ignition source, a viable one for any of the refrigerants, they will ignite. You have different consequences. So the industry has been learning how to handle what is called these 2L or lower flammable refrigerants. And where we're at right now is the product and application standards are nearly complete. And what remains is once those are issued into the building codes, the adoption of building codes. So a lot of people talk about, to me, I'd like to adopt R32 as a replacement for 410A, or I'd like to adopt 454B. And you see these announcements for 410A replacements. People go, I want to buy a product today. Why don't I see them? Well, it's really around the building codes. How do you apply something that's flammable in a building without the design requirements or the details about how to apply it? Now, what's going to happen here essentially is when you have a flammable refrigerant, you need to control the charge. So the charges will be restricted, and you'll have to do something about sensing in some cases if the refrigerant charge is large. like for equipment rooms today, when you're using even non-flammable refrigerants, you have a lot of refrigerant in there that's low toxicity, like an A1, but you still need detection and ventilation. So you'll see more adoption of detection and ventilation if the larger flammable charges are used or you need to use them. So the technology around these is kind of interesting. So we'll talk about that as well, what the available options are. So next slide, please. So people always ask me, I get emails every day, how and when will the US do the HCFC Phasedown? The good news is last December, as part of the AIM legislation that was put in the omnibus bill in December, it forced the EPA or required the EPA to come up with some rules around HFC. And the industry supported it along with both Republican and Democratic members of Congress because it's an ability to allow the industry to innovate. We have technology ready, and we just need to move these things forward with having some common sense rules around how we're going to transition and when. So April 30th, if people were watching, the EPA issued a proposed rule to reduce HFC production. And as part of that proposed rule, by July 1st, they'll be issuing a rule for comment. And then by October 1st, as part of the legislation, so they can't really fool around here. By October 1st, they'll have a finalized rule. So within the next few months, we will have the details of the phase down, at least to beginning to out to 2024. And the next slide, we'll talk about that. But right now, what they're going to go for is a 10% reduction by 2022. And people are saying, well, how do we do that, Steve, from the baseline that occurs in 2011 to 2013, as it says above? Well, that's pretty straightforward. We already have a lot of YF in cars from 134A transition. We already have some low GWP fluids for foams that are already out there. So the US has already phased down well below 10% already of the 100%. So that's a phase down to go from 100% down to about 15%. You'll see on the next slide. So they're really seeking comments on how to get that first big jump from 100% down to a 60% level or a 40% reduction. So next slide, please. So this is what the phase down looks like graphically by GWP on the left-hand axis, which is each country has their own GWP bucket or average of gases, or a basket of gases, some people call it, versus time. And what's on here is you can see what's happening in the European Union, which is the blue line, which they're ahead of the United States and other developed countries. And so we see some, behavior and understanding of marketplaces of what, things are being adopted. But the red line is really what is interest to people here locally in the United States and Canada for that matter too. I mean, Canada will be following the same rules. Different basket of gases, probably similar rules, similar timing, but not necessarily the same. Because there's not a lot of air conditioning that goes on in Canada compared to the United States, where a lot of the basket of gases is around air conditioning. So they're seeking comment for 2024. And then after that, obviously, as the phase down goes, they will learn from that. To get to the next step, there'll probably be new rules put out there in 2024 to hit the 2029 phase down. So this is a much more complex phase down than the ozone depletion potential Montreal Protocol, where they just banned chemicals. The good news is why they could ban chemicals if we had substitutes already known. So like R12 went to 134A, R11 went to 123, R22 went to 404A, or 502 went to 404A, and R22 went to 410A. So we had known fluids, and actually a lot of these fluids had lower GWP than the CFCs. For example, I think R11 is around 5,000. So 123 is like less than 100. So, I mean, we already did some phase down already indirectly without knowing it with the new refrigerants. But you can see we're going to, all of the refrigerants are available for use. We're not going to zero. We're going to go down to about 15%. And if you want to build the slide, please, there's some couple builds in the slide. So, one of the targets, you can hit the button again and just build it out. One of the targets is, whoa, go back a slide, sorry. One of the targets is, you'll see as people are putting limits like less than 750 GWP on replacements. So when the rules come out, it's going to be pretty obvious that for 410A replacements, they're going to put a limit about 750 GWP, excuse me. And then my dog's barking. And when you look at chillers, they're going to put a GWP limit of 750 because the technology exists to go below those limits. Now, when you look at the future, that 15%, the average has to get down to about 300. So eventually, as technology develops, can we get below that 300 limit and allow growth going forward? So currently they're shooting for 750 because the technology does not exist in all sectors, product sectors, to be able to allow a less than 300 GWP transition. Next slide, please. So what's going to be available now and what's going to be soon to be available for lower global warming refrigerant options? Next slide. So this is a really complex slide. It's got a lot of plots on here, but I think what I want to get across is if you want to start building the slide, we have a limit of 750 is what we're looking for on the left-hand axis. And all the blue dots are non-flammable refrigerants. The red squares are 2L refrigerants technology that's available. And along the axis there is CFM per ton, which you'll see if the slide builds. Mohammed, if you want to build the slide. So there's the 750 line. Let's keep building. There's the line kind of between flammable and non-flammable as we go across CFM per ton for various displacements, and just keep building the slide if you would. So we have solutions over here like where 123 is. We have a lot of non-flammable, very low GWP blue dots down there. So we have great options there. Keep building the slide. When you look at 134A, like, yeah, we can get down to 300 to 600 or so. So we can get below that 750 limit and still have non-flammability, but we can't get to a GWP below that and stay non-flammable. So I have to start introducing 2Ls like 1234ZE. And to keep building the slide. So we look at 404, like, yeah, we can get down to about 12 to 1300 with non-flammable replacements. So we'll have some good interim options to be non-flammable and put into products and retrofit products, which is important too. But then after that, we have to go flammable. And if you look at 410A with the last build here, really we have to jump right to flammable refrigerants around 410A. So one more hit there, if you would. And the problem here though with 410A is we don't have a non-flammable lower GWP fluid. So products will be on rooftops, and other 410A products will likely be stranded with that refrigerant, and you won't be able to retrofit to something lower. You cannot put a flammable refrigerant in a non-flammable piece of equipment. So the product standards and the codes won't allow it because of the requirements that are needed around certification. So last build, if you would, please. So we have nice alternatives around 123, all less than 10 GWP. They're non-flammable, so they're adopted in the marketplace, and we'll talk about that. 134A options, we have 300 to 600 to be non-flammable, so they can be adopted easily. And they're available in the marketplace today as well, both in the United States and in Europe. 404A replacements, we're in that 1200 to 2100 GWP. There's a lot of different options that are non-flammable, but people are using today. Putting in existing equipment to replace 404A. You look at 410A, you don't see a lot of activity because the replacement options are 2L. And so new products, new standards, special designs, no non-flammable options. Now today you'll hear, you've seen in the announcements, Honeywell announced some work with Trane Technologies around 466A, which has got a GWP of just slightly less than 750. It's non-flammable. This is an experimental fluid we've been playing with, a new technology. So we're looking for some, possible options to get ourselves to phase down non-flammable below 750. So some of the challenges there with the new fluids, in this case is we have chemical stability, materials compatibility with 466A that we've been working on for the latter part of less than about 5 years. And so it's some great innovation. Whether it makes it to the marketplace or not, I'm not sure. So it has other, timing-wise availability. Thanks. So moving on to the next slide. Let's go deep dive into some products. So you're looking at large water-cooled chillers, usually centrifugal in type, 123. Some people sell 134A in this equipment. We have some great lower pressure options, not 134A like, but more like 123 like. So you look at these options, they're all non-flammable. They have really low GWPs, so they're high efficiency. So if you look at the chart there, we have relative capacity, but the efficiencies are all plus or minus 1 to 3% of each other. We have some good near design compatible alternatives. So like with 123, we have 514A, which is shown there. It's really close to capacity 123. So those designs are forward and backward compatible to preserve customers' investment in their equipment. A lot of people are going to 1233 ZDE, which has got a higher capacity, so requires some ASME design conditions. Good refrigerant. It's also used in foam blowing applications to replace 245A and high efficiency foams for like refrigerators and other things. And just emerging is this new molecule. It's a little higher pressure. It looks more like 245FA if you want to look at the center line on the bottom axis and capacity, but it's just emerging as well. So 514A and 1233ZD have been in the marketplace from anywhere from 5 to 6 years already, and they keep emerging more as we get closer to those phase out dates. Next slide, please. So when you look at little smaller chillers, maybe screw, centrifugal as well, maybe some larger scroll stuff that people do in this area for compressors. It's mainly 134A replacements. So we're looking at air water cooled chillers. So you have some limits around flammability. If you want to get stay non-flammable, 300 to 600. If you want to get below 150, if you want to use 150 as a target, you become flammable. The refrigerants are good efficiency wise. You have some near-term design compatible, so they're forward and backward compatible, so they preserve the customer's investment in their equipment. That would be 513A. It's a non-flammable GWP around 600, so it's below that 750 limit, has nearly the same capacity. ZE, 1234 ZE is a flammable refrigerant. Its capacity is much less, so its operating map is a little different than 134A. Yeah, you can do the cooling, but you can't make ice very well or refrigeration very well. So, that is some of the trade-offs. So you look at 513, which is a replacement for 134A, and you want to look at 515B, which is starting to emerge in the marketplace. It's non-flammable. It's like a non-flammable ZE with a GWP of 300. So that gets you out to that 300 limit that I showed earlier and could be long-term sustainable. So, a couple of good choices. 513A is already in the marketplace. 515B should be emerging. ZE, once the building codes are updated, will be emerging in the marketplace as well. These items are in Europe already. Excuse me, I have a fly. We should see those shortly in the next few years. Next slide, please. So when we're looking at 404A replacements, things get a little more complicated because we have more solutions and there's more blends. Basically blends of R32 blended with some of the new fluorinated HFO low GWP fluids. And so to get the capacities right, we end up with these more complex blends. So you have non-flammables with GWPs anywhere between about 1300 and 2100. And they're design compatible to some extent with 404A, so you can replace, if you don't have a flooded evaporator, you can replace these fluids in place of 404A. Because they're temperature glides of these fluids, there's some temperature glide around that, so getting approach temperatures in a flooded evaporator just aren't ideal. Now, the leading flammable refrigerants get you down lower in GWP, and it's kind of a potpourri of those. They haven't really decided which ones are the best because there's more innovation going on in this place. And the one thing you see from the bottom end, I would call it in capacity in this area, is you see hydrocarbons gaining popularity in fractional tonnage or fractional horsepower products, bottle coolers, humidifiers, things like that, where the refrigerant charge is very small, so you don't have any issues with the flammability controls. So it can be a hermetically sealed product. You don't need detection because the charge is so small, you get a leak, risks are low. So issues here, glide is high. They don't have, 404A has a low glide. It replaced 502, which was azeotropic. We don't have another 400 that has low glide. So there's a lot of innovation, a lot of redesign that has to occur here.
Actually, Steve, can I jump in real quick? It's someone in the chat asking, what is glide? So can you define that?
Yeah. Yeah, I can handle that. So, when you have a pure fluid and the as you enter a heat exchanger and it evaporates or condenses, you condense at one pressure and one temperature across the heat exchanger as you're putting air across it. So when you have a blend of refrigerants, some things have higher boiling points, some things have lower boiling points, and the glide is the dew point versus the bubble point. And so as the refrigerant goes through there, you're condensing one refrigerant preferentially versus another. And as you go through that heat exchanger, there's more resistance, right? So that either like in a condenser, you're trying to condense one component that may be higher pressure, one's lower pressure. You have to drive up the pressure or the delta T across the heat exchanger to cause that condensation to occur. The reverse happens on the evaporator. And so your lift, what your compressor has to do, right? And what your temperature approaches has to do grows. It hurts your efficiency, it hurts your capacity. Usually you can design the equipment with bigger compressor. But that temperature resistance between that glide, temperature glide, across those heat exchangers drives the inefficiency around them. So, you know, you would like to have fluids that have no glide. Now, some people will say, okay, Steve, you said when you have presentations, a small amount of glide can be beneficial. That is true. So you have a really small amount of glide, say a few degrees F between the two boiling components. The condenser resistance a lot of times is less than the evaporator benefit, temporary benefit around pressure drop that comes through the heat exchanger, and you can actually get a little benefit. But once you get too high a glide, it is an issue. So from a designer standpoint, it's like, you know, take your pillow and blanket and go to bed. If I have no glide, design, get good approaches, don't have to deal with fractionation of the materials. And so, yeah, it's in the past, people, in the last transition, we had some glide blends with some glide, you know, 1, 2, 3 degrees. People didn't understand it. It's really confusing. We're going to have refrigerants, you know, with 8, 10, 12 degrees F of glide. And so the resistance across the heat exchangers can be great. Now, designers like ourselves can hopefully reduce that amount, but it is a resistance that costs us efficiency around the heat exchangers. So I hope that helps. So we're looking at, you know, transitional fluids, which will transition to internally and then get to long-term solutions later. We still need some innovation in that area. It'd be nice to have a low glide, low GWP fluid. Even if it was 2L, it would still be of some advantage in this area. So now the favorite place everybody talks about to me around is 410A products. So next slide. So a lot of people see, you know, you see announcements by various OEMs around refrigerants. We're going to use R32 as our next fluid. We're going to use 454B. You know, these are going to be interim fluids because their GWPs are, you know, 32 has got a GWP of 675. 454B has a GWP, which is better, 460. But, you know, it still doesn't get you to that magic number of less than 300. Ideally, life would be easy if I could get everything less than 10, but we can't get there. So that's why it's a phase down based on technology, available technology. Now, 32 is a pure fluid, and it's basically 410A without 125 in it. 125 is added to 410A to make it non-flammable. And so they remove that and you have the pure fluid left. 454B is simply R32 diluted down to match the capacity of 410A. 32 is a little higher capacity of 410A with 1234YF, which reduces the GWP without much impact on glide. So those are the first two fluids people have been announcing. Now 466A, like I said earlier, is a non-flammable. It uses a new fluid with a GWP of 1, trifluoroiodine. It's an old fluid with renewed interest because its global warming is so low and its atmospheric life is so short, but it's also non-flammable. So when you blend it with R32, you can make R32 non-flammable. So that's been the interest on this. Now, of course, iodine products are much like lithium. You need to create a supply stream from. There is one, but it needs to grow. So I think availability will be limited at first around that. So the efficiency, the good news here is the efficiencies are usually greater than 410A in many cases. And they're all near design compatible is what I call it means. So the capacities are very similar. Small redesigns are needed. Glides are small. 1 to 2, maybe 3 degrees F with the 454B. 32 obviously is a pure fluid, no glide. 466A is around 454B. So you don't really see impacts on design. But once you get below 300, we're really working on innovation in this area. But like I said earlier in my presentation, what's really holding up the innovation in this area is just getting the flammable or product available, the flammability updated in the building codes, the product standards. And so we're close, and we're on schedule to hit that 2024 number. Might be a little later on some cases, might be a little earlier. We got to get the states to up their codes as well. There might be some resistance there potentially. Some people operate in very, very late or very not up-to-date building codes in a lot of states. So that's something you'll have to watch out for, is will the building code get updated in your state or jurisdiction? And will there be any resistance to using flammables? Shouldn't be. I think we've done a lot of research. And we've assured ourselves that reduced refrigerant charges, that'd be good, and detection is good. So that's all being incorporated. Yes, so I see I see somebody asked about 410A pressure in the chat. Yeah, these are very similar to 410A, but you can't retrofit it into a 410A piece of equipment because these are flammable. 466A would be likely to be retrofittable, but not available at this time. So just in conclusion, the EPA is going to regulate HFCs this year. And so we're going to see some cap, what it's called a cap. So they're going to take a baseline and start of how much basket of gases they have and start phasing it down. So you're going to see refrigerant prices go up because availability of supply as things become more restricted. Lower GWP refrigerant technology has matured enough to allow an interim phase down. So I think we have the technology. We can get that 40% down. We can get that 60% down, and maybe even that 30% down 70% with what we have on the plate today. But to get that last piece, we're going to have some more innovation in the 410A and the 404A space. I think there are available in the low pressure area specifically to replace 123. We have the long-term available options. They're non-flammable in the large chillers, which is good because we have large refrigerant charges, and we put these in equipment rooms primarily. We also see small portable equipment using hydrocarbons. Those are going to be long-term options. You can also see some of the adoption of 515B or 1234ZE, depending on the application, will be long-term options in those medium pressure 134A options as well. And I already talked about that one bullet. So, realizing this phase down, we have to fully understand the flammability risks. You need to put products in the field. You got to have situations occur. We can predict all this, or we model this stuff, but until somebody misuses the product or misapplies the product, we haven't fully realized what is flammable. So in the past, we've been using non-flammable refrigerants. So if you have a lot of leeway when you have an open torch or you're doing repairs on the unit, if a person's not following the procedures per the manufacturer, per the standard, is there going to be an incident? And trying to under how many of those incidents are going to occur. So I think that slide completely built out, Mohammed, I think, or is it not? Cool. And what you're going to see more too, and you can actually see from my presentation, we have a lot of different refrigerant options. We're going to have a lot of different interim fluids and different products, and you're going to see more product fragmentation for applications and more choices for people to choose from until further down the road when there's some standardization may occur in the marketplace. But at first, you're going to see, like in a 404A space in the supermarket, right? You're going to see hydrocarbons being used in small capacity areas. You're going to see other refrigerants used in distribution systems. Rooftops may start with a refrigerant like 32 or 454B, transition down to a different fluid. So and when the phase down occurs, it's going to be interesting to see what behavior occurs around the pricing of refrigerants, because it's going to be based on a global warming potential and cost of carbon at some point, and so you'll see some volatility. We saw that in Europe. We saw a lot of volatility until people transition, and then it became more stable. So that should conclude my talk. Oh, yeah, one last thing. Thank you for building that out. I think this interim cycle is going to last anywhere between 8 to 10 years. So it's going to take us from 2024 to 2034, maybe 2032, maybe 2036, and then we'll see maybe some final solutions or long-term solutions in some of these sectors I talked about. Thank you for your time.
Thank you, Steve. It was great. Too much to digest for sure. But I'm happy that this is going to be a great resource for everyone who's going to just dive into CLF portal. So yeah, I mean, thank you for the great presentation. And I ask you all to just, if you know a group of MEP teams and designers, please make sure to share the recording. This is going to be really valuable for that transition that Steve mentioned. So with that, we can switch to our question. And if our panelists can turn on your camera, so we can, I think you all have your camera on. Don, if you can turn on your camera, great. If not, that's all good. So my first question is for our design engineers in the call. That I know you all had some experiences pushing for these replacements for R410A and others. Could you share one or two of your experiences with us and just tell us the stories and the lessons learned that you had? And we can start with Joe with WSP and continue with Elara team.
Well, some of my pieces have been to actually retrofit from older refrigerants into even 410A or some of the other refrigerants. And one of the questions is related to the question I asked Steve earlier about pressure conditions, because we were running into pieces where the equipment wasn't rated to handle the pressures, and we were having a lot of clean out pieces. So it led to extended discussions about whether it was easier just to replace the equipment outright than to try and retrofit these pieces. And so that was one of my big pieces or hurdles in retrofitting for refrigerants and moving and transitioning there. Another
Joe,
one
you were talking about R22 going to 410A or some other pressure, right? Yeah, that was a transition. You know, can you use the interconnecting hose and then tubing and all that stuff, right? I mean, the vessels themselves are not rated for that higher pressure, right? So, you know, you basically have to change the components, right? If you're gonna retrofit. Now, can you save the interconnecting lines? I think the industry found out, yeah, you can. If you're going through all the walls and stuff, you're kind of like, yeah, it's kind of hard. But that's straight copper tubing usually, hopefully. So it can handle the pressure, but the equipment, right? Yeah.
It was the equipment, and then they even got into the brazing materials.
Oh yeah, because the braze joints and how they're designed and what the braze material yield strengths are and all that stuff. Yeah, that was quite the challenge in that transition. Yeah.
Right, and so that was our big challenge on the one where we were trying to do this on several coils around the building. So
right.
Yeah. Brian, how about you?
Well, we will definitely evaluate these scenarios on a case-by-case basis. A lot of the equipment that is R22, I mean, if you're looking at changing out the refrigerant, you definitely want to weigh the cost of replacement. So that a lot of the R22 equipment, due to the nature of what equipment used, R22 is really at the end of its lifespan. Another challenge I think is the oil, whether it was synthetic or something along those lines. We found would factor in on the ability to upgrade it. But the reality is we still find the R22s available. For the repairs, the compressors may have to do a little hunting. You could still find them. So if they want to squeeze a little bit more time out of the equipment, we're finding they're still able to do that even with the R22 equipment. But realistically, they should be planning on an equipment replacement for that. And I think a lot of the bigger equipment that you do want to really go through that level of effort, it hasn't really come up yet.
Don, do you want to add anything to that? Todd. You're on mute. You're mute. And thank you for making it.
Yeah. I shared with everybody on chat a very good study that was commissioned by the city of Seattle on leak rates. And I'd encourage people to look at it. And they get down in that study of the probability of leak rates depending on fittings, flare fittings versus braze fittings, and so forth. And come up with a whole bunch of different scenarios over a 30-year life of a system. And so anyway, I shared that link on a chat. I thought, for that'd be informative.
Yep. No,
thank you for sharing that. That is one of the challenges we've had in the industry, is trying to understand what are the average leaks. And there's an average, and that average is full of a lot of different things, right? So over the life of the equipment, right? So you can have I think a lot of people think there's a low leak rate that occurs all the time. It's really not a low leak rate. It's a combination of various leaks. Yeah, you can have low leaks, but there are catastrophic leaks. I'm thinking, residential homes, right? I like your comment on flare fittings. I wish we could ban flare fittings, but for some reason the industry just wants to keep using them, even in flammable refrigerants. We had a study that they leak. I'm like, just get rid of them. My chief engineers are like, please, you can't do that. Stop talking like that. I'm like, so you didn't hear any of that?
Right.
Because I had a flare fitting in my house on my unit. I'm like, why is somebody putting a flare fitting on my residential unit? I'm like, should this be brazed? I'm like, jeez. The guy was surprised I knew it was a flare fitting. I'm like, I'm assuming this leaks, right? So eventually, I've owned 4 houses and I've had 2 catastrophic leaks. One of my tenants stepped on the line and broke it, right? The other one was just a corrosion failure and it gave, so, okay, I have 100 units. That's a 2% leak rate over its life, right? By 2 catastrophic leaks. So if the average is 4 or 5, right? Then it's a bunch of other things, so we see based on how much refrigerants bought in the field, it's somewhere between a 4 and, if you look at unitary, somewhere between a 4 to 6% leak rate, but I think it's a mixture of different things. I'm really curious to read the city of Seattle's thing, because this is data it's hard to get.
Right.
Because we do a lot of in-warranty work. Well, that in-warranty stuff doesn't tell us a lot.
Right.
Yeah.
Right.
On root cause, other than Trane, you're responsible because we were low on refrigerant and we filed a warranty claim. It's like, don't tell us what happened. We did a repair. Where? What was it like? Was the unit damaged when it got there? Was it installed poorly? Was it, somebody step on a line, somebody crush a line, stuff like that. Vibration failure. Yeah. Stuff like that, yeah.
I mean,
hey, Mohammed, I think I've got to get off as I have a funeral I have to go to. So great presentation, Steve, by the way. Thank you.
Thank you, Don, for making it.
Okay.
And with I mean, also I like to give a kudos to Scott for eating a veggie lunch, which is contributing to the intent of the events, and also for asking great questions. I mean, with that, I'm changing the sequence of my question. I like to get to the barriers that we talked about, leakage, and we have maintenance issues. I mean, the building engineers and the industry is not there yet to kind of take care of the issues with these new refrigerants. The leakage also from different type of refrigerants is also important. Like something like ammonia can cause, the leakage from different refrigerants can cause different issues to air quality or like exposure to toxic ingredients. So what are the I mean, this is a question for everyone, and I'm sure Steve has more thoughts on it, but this is a question for everyone, that what are the barriers and challenges that you see for these kind of 8 to 10 years transition that is already happening, and that's our standard goal, a standard practice goal, but we want to just do that more immediate, but we got to take care of these challenges and barriers. So what are your thoughts and like feedback on these type of challenges?
So I think the big one is going to be on getting manufacturers able to produce equipment and even the refrigerants that work within these hit that A1, A2 window that Steve referenced early in the presentation, like that, just ramping up to have that equipment and those refrigerants available for hitting the 2024 start date. You know, there's going to be the big scramble, and it's going to be similar to every time IACC comes out with a new standard for equipment efficiencies, and then everyone's scrambling to update their literature and change the COPs and get their tests done for the new COPs out and all that on their equipment. It's just going to be the same, but for these refrigerants. And so I think it's not necessarily a barrier. It's just the next challenge that comes along. From that, and then also the training, that's going to be a big challenge to get everyone retrained if there are new pieces that have to come along for the maintenance people, because you know sometimes a maintenance guy will do something new as long as his father did it before him, and so you have to work that out.
Oh, I'm glad you brought up training. So when we surveyed EPI, which is AHRI for Europe, their biggest issue after they've already done some transition is training for technicians. There's still a gap in Europe, and they're the best trained. And they have all these programs, right? So this is going to be, we even see it in our workforce within Trane. It's like, okay, we're going to have to do things differently with flammables, right? So can you unlearn, I hate to say laziness, but the comfortability of, I have a torch, I have refrigerant maybe around, I'm okay. I haven't had an issue. Whereas, you know, I might have to have a leak detector laid on the ground to know I have refrigerant on, because you can't smell the stuff, right? So, yeah, it's going to be, in Europe is struggling. I can't imagine what the United States is going to do. I can't imagine what, you know, maybe 20 years from now in Mexico transition, maybe it's not a problem, but I can't imagine it's all that unlearning of handling safer, well, basically I always say pillow and blanket, go to bed refrigerants. Really, you don't have to worry about anything.
Right.
Great.
You know, I think coming from the design side, one of the challenges is anticipating how these changes are going to impact equipment. A real good one for me is, you know, we were looking at a building that was looking to replace their PTEC units. You know, they didn't have money to upgrade their building, but it was coming at a time when our 22 was phasing out, and we didn't have the equipment available as the replacement. And the thing about PTEC is they're standard size sleeves. So, you know, one of the challenges is, well, what do we do? You know, we're going to put in new sleeves, and you know, now is it going to fit? You know, so you have to just anticipate a little bit to really, you know, project, you know, how that's going to change the equipment for your clients.
Yep. Great. So with that, we get to the next question, which is my favorite question because it's more related to my daily job, is kind of like measuring the impact of the different refrigerants. And so we are in the world of decarbonization now, that we have so many regulation and standards and codes that advocating for decarbonization in the building industry. And I had one slide in the beginning specifically to tell the story that thinking about carbon emission in the big picture, like other than operational energy and the embodied carbon, carbon emission from refrigerant is a big part of the story. And how we can, the question is really that how we can make sure that we can implement, and this is maybe going to be a tough question, and I would say if anyone else also in the attendees have a thought, you can chat in, because that's where we can tell the story, how we can measure that. And this is probably going to be a good question for Steve, that measurement, how we can do the measurement with the, we have all these values, you showed that in your slides, that we have all those measurements in hand and we can measure that. But what you're going to see that happen in that world of measurement, how the how measuring the carbon emission of the refrigerants can help us to make the story and just like push and advocate for greener refrigerants in the market.
Yeah, I got to get off mute first. So, you know, what you see from my talk, I hope you realize there's like this technology gap, right? Lower pressure refrigerants, medium type 134A, you can get the low GWPs, right? Higher refrigerants, yeah, I can't get all the way down. If I got down to 1 or 10, right, it's like I can leak and there's no contribution. I mean, it's you know, it's a pound for a pound, right? It's not a pound for 1,300 GWP like 134A. So how do you get there? Well, you may have to take a different approach from your design, right? So you want to put a VRF system in, it's going to use 410A, okay, and it's going to use 32, 454B. Yeah, I can only get to 460, 675. I'm doing that for tomorrow. This system will last 35 years. Well, maybe I need to get redesigned chilled water. We're going to do electrification of heating, right? At some point, maybe there's going to be some of that coming out, you know, with chillers, being able to do electrification of heating. You know, maybe you take that approach. And I'm not advocating that. I'm just saying, you know, you look at what you have on your plate today. You know, tomorrow, if somebody came up to me and I have an A2L that's GWP per run as 410A like, or near, I'm like, yes, touchdown, we are there. Refrigerant emissions are completely, you know, out of the discussion, right? To a large extent. So then you just got to worry about efficiency and product cost, safety, and then those things I think can be managed depending on how much cost you want to throw at heat exchangers, things like that. So I think hopefully we need to, you know, if we can get to lower GWP fluids, then you can just take it right off the table and the refrigerant discussion and go, well, now it's really down to what secondary environmental impacts does it have when you leak out? Do you really want that chemical in the atmosphere when it rains out? You know, what are those breakdown products? You know, you look at that level and the GWP is gone completely from the equation. And so then you're just focused on electrification of the grid, electrification of heating, those things where you can really make those big reductions, right? I mean, if you look at some of the charts I showed, the refrigerant was like small on top at times. Then it's basic electricity use or fossil fuel use for heating the building. And if you can drive those down, then that's really where you get your big bang for your buck. But can you what I've been doing for work is how do I marry refrigerant technology with electrification of heating and having those options and new technology and try to get those things to work together, right?
Yep.
Sorry for the long-winded answer.
No. That was. I think this is going to be. I mean, to me at least, this is going to be a driver of the conversation and what's going to be really useful for all of us. I had a follow-up conversation. Actually, I had a follow-up question for the design engineers, for Joe and Brian, but which was, have you had any experience with your clients or your projects that you had to kind of do some trade-off analysis between, like for example, going for something like VRF? I mean, it's a more efficient system. Your operational carbon emission going to go down, but you're not quite sure how much increase you're going to have in your carbon emission from the different type of or different usage of the refrigerants. And as Steve mentioned in his presentation, that we already have some replacement for our R410A that is more efficient and in efficiency, and also it comes with a much lower global warming impact. Do you have any experience to share on that you had to kind of like talk with the clients about that trade-off, or just like the story between those two part of the carbon emission?
Well, we actually recently just did a presentation about a conversion that we did over at an elementary school, and a question came up. At the time I couldn't answer it, but you know, what was the refrigerant contribution to the carbon emission rate? So you know, just going back and looking at it, you know, the building as it is currently operating before the renovation, somewhere around, you know, 600 tons of carbon emissions, not accounting for any sort of refrigerant. It's all small kind of unitary window units. And with the VRF implementation and with the other systems that we were putting in, we were bringing the emissions down to about 250 tons. And that's with the electricity grid as it currently is. We would anticipate that to improve as renewables, grow. Now, if we're accounting for the carbon emissions due to refrigerant leaks, we were figuring that it would be another 8 tons of carbon contributions due to the refrigerant leaks. Part of our analysis, we also compared it to a traditional boiler chiller system, and the carbon emissions due to the energy is actually even higher. So the VRF, when you were accounting for the refrigerant leak rate, is about 270 tons. And the traditional system would have been 286 tons of carbon emissions annually. So we're still actually, even with the trade-off, we're still performing better as far as the carbon emissions go. So, obviously we would want to, eliminate that aspect of it, but I think it's an important part, of the evaluation that really should be considered.
Yeah, no, definitely. Joe, do you have anything to add to that?
Mine comes from the other side, where I've had real hard time making a carbon reduction argument for different systems as the sole part of a discussion with an owner, especially when a lot of people are motivated by cost motivations. So it's hard to, talk about the global emissions. You use that and then lead to, well, things are getting more efficient. You're going to have a better operating cost, but also you'll, as we move on, you're going to have a better operating cost for like maintenance. People are going to be trained on the newer stuff as opposed to the older pieces, especially if they're looking to try and retrofit or maintain old pieces. So that's doesn't quite answer your question, and it's not all that helpful. And I'm sure more people are more golden tongued than I am to convince owners that to do it the right way. But that's my reality that I'm having right now.
No, that's actually that's a good transition to my next and last question before we move to Q&A, and I see some hands already risen to ask question, which is it was really good to hear from Steve on how our standard practices and codes going to get upgraded soon to push for a market transition. And I'm sure when EPA upgrade that code in October, we're gonna have a strong market driver. But I think and a lot of people in the call now, we have from sustainability consultants and people that advocating not only for a standard practice, but for best practices and for greener buildings that are like above average practice in the market. So the question is, like, maybe like 10 years ago, achieving the enhanced refrigerants in LEED was a best practice, but I don't believe that's a best practice anymore. That's average, a standard practice. So talking about the market drivers that are going to help us in the next 8-10 years, other than these codes that are going to push the transition of market, and this is kind of a brainstorming question, that do you feel that we should go out and advocate LEED to add a credit that talks about the carbon emission of refrigerants? Should we ask like cities to add that to their stretch code? Like, what we can do to establish that best practice in addition to the standard practice that EPA and others going to help us to identify? It's a tough question, but it's something that I'm sure is going to be useful to discuss for a lot of people in the call.
I can jump in. I can jump in here if you want.
Yeah, go ahead,
You know
Steve.
what's, you know what's interesting in Japan, because they have limited electricity over the last 30, 40 years. What they implemented was so many kilowatts per square foot, right? And so what that forced was the market, believe it or not, to go to direct fired absorption systems, right? So you only have so much electricity. So my thought process in my head was, can you put a carbon measure on a per square foot, right? And it would force you to think outside the box and allow adoption, right? Rather than like a LEED certification. If a federal government or a state government came and said, this is all you're allowed per square foot in carbon emissions, and how you get there, right? And you can take some futuristic looks at how the green's greening and all that stuff at the same time. So, you see some municipalities and states going, you're not going to have any more fossil fuels in new buildings and stuff like that. I mean, that's one way to regulate it, but another innovative way, it's like how many carbon emissions you get per square foot. And I think that would drive people like, well, I'm going to have high efficiency line, better insulation. I mean, I'm going to take those trade-offs, right? And refrigerants, to me, should have like a little penalty on them, a little higher, so that it drives people to, I'm going to get to the lowest GWP possible here and have that turn. So this is just something when I see stuff around refrigerants and I see different marketplaces around the world, it's like, how do you drive that behavior, right? Like you were saying, Joe, I'm a salesman so far, but I can't sell increased costs with no benefit. I think you almost have to force in regulation to some extent, mandatory regulation, just like equipment, minimum efficiency standards. It's like building minimum efficiency standards and get this much carbon per square foot, or whatever you want to look at it that way. So, I mean, to me, it's like that would force people to think a little differently in their carbon budget, I would call it, right? Your budget of carbon. Embodied and total, just kind of throwing it out there as an idea. It's probably already happening. I'm probably not even aware of it. So.
I think Scott had indicated their firm's working on implementing a carbon line item in their comparison tables, and I totally agree. We've been doing something similarly. Oftentimes we're focused in on the energy, and historically we've been, you're looking at how much energy you're reducing, how much cost you're reducing, but you tend to ignore, presenting data on carbon emission reductions on specific measures. So we've been including that. I think that is certainly an important, as we move along, accounting for the refrigerant contribution to that would provide more information and give you a much more realistic aspect of it, especially when people are really trying to strive to make those decisions. Joe had mentioned cost is always the big thing. First cost specifically is always a big driver, but as we go along, I think that'll change, especially depending on your client.
And I've been mulling over what you said, Mohammed, about how LEED, when LEED first came out, it was sort of aspirational and a target and a reach, and then that's sort of become baseline, easy walking to it. And so to pile on Brian's idea of using more of a carrot and aspirational, we talk about carbon in our SD narratives or SD discussions with the owner for scoping pieces. And then if some of these different certification programs use even have gradations or something like that for different LEED points, you could get, it would be a little more of an aspirational reach piece for people. Would work. And so you'd have the stick from Steve's idea combined with the carrot of aspirational certification points. Might work.
No,
I don't know, but
No, that was great. I think I think that's what we all need to kind of know what's what's helping us to make a conversation with the client. If you want to just define something beyond standards, like how we can drive that conversation. So Scott had a question earlier in the chat that I think was a really good question, and I don't know if we addressed it or not, but we didn't talk much about the embodied carbon of the refrigerants and what it takes to manufacture them, but he had a question on what happens to all the R410A that we had in the market. And I want to turn that to a bigger question that just like how we can, like, is there any data to, I mean, Steve, that's a question for you. Is there any data on the embodied carbon of the different refrigerants? And is that something going to be out there soon that we can utilize when we do a whole building LCA, that we can incorporate that into the analysis?
Yeah, so I was just trying to find his question so I could read it and see if I, this one by Scott Farman.
Yep.
Farman. Yep.
Yeah, he had a question on like saying that what happens to all the R410A. Yep. Scott, do you want to?
Oh,
you're on mute.
Scott.
I think you are muted from your microphone other than Zoom. We can still hear you.
Oh, now he's muted again. Let's try unmute it again. There you go. Try now. Nope. Well, you know, so you look at refrigerants around the installed base. A lot of times, you know, there are requirements for larger charge systems to reclaim and recycle that material, which then is resold back into the marketplace for existing stock, right? You're not allowed to manufacture more, for example, R22, right? I mean, that's the big thing right now. We're really scarce with R22 right now. We've reached that kind of tipping point. There's a large install base, but there's, you know, a price for that. Personally, when you look at 410A, 410A has two components, you know, 32 and 125. The 125 is the high GW component. It'd be nice to be able to separate those and bring the 32 back into the marketplace and new equipment and slowly get the 125 out of the install base. You know, the EPA assumes once a pound of refrigerant is sold, it will be emitted over its lifetime at some point. So whether you, and if you think about it, you keep doing the reclaim and recycle and you lose a little bit every time, yeah, it's all going to be emitted, or it's collected at the end of life. And then, you know, there's strategies, different states, you know, like California has, you get the price for destroying things, you know, for carbon and offsets and things like that. And that's really what you have to do to get rid of the carbon emissions from embodied carbon and refrigerants that's been sold, it's in an installed base. Is if you can't retrofit with a lower GWP fluid and destroy the other refrigerant, or repurpose it, I call, right? Repurpose the refrigerant to do something else. So separate the 410A, 32, 125, get rid of the 125, keep the 32, keep using it in blends as we need it, as we move forward, keep repurposing it. And at some point, you know, if we don't use 32 anymore, you know, phase it out and destroy it as well. Not being specific of any refrigerant, just an example here. So how, you know, that's really, we're gonna be stuck with this for a long time because we have a large install base, even of CFC units like R11 still with high GWP, and you know, and people just refuse to give up their old equipment, right? I mean, I saw a 50 plus, maybe it's longer, man, R113 unit. That was before I was born. We stopped making those, and I'm 54 years old this year, so it's sort of like, okay. People, you know, this install base is still there, right? If they discontinue that equipment, somebody reclaim and recycle it, put it back into some stock, they use it for something else. And so we're going to have that pile of gases that we continue until we start thinking a little different about this embodied carbon around the refrigerant, how we incentivize it, how do we get rid of it, how do we repurpose it? You know, a lot of people like to destroy it, and I'm like, well, in chemistry, you should be able to not destroy it, transform it, right? Take the chlorines and fluorines off, you reuse them for something else. Believe it or not, you know, a lot of people eat fluoride every day, right? And you brush your teeth, you have salt, you have a lot of drugs use fluorinated functional groups on them, believe it or not, when you take a pill. And so it's like, you know, so all around us, we should be able to repurpose those back into not venting the atmosphere, but yeah, it takes energy, right? It takes innovation, but we should be able to repurpose this stuff back into something. Because these are fundamental building blocks. They're simple chemicals, right? Hard to break apart, but simple chemicals.
Yep, and I think that's going to be like for a couple of these new low GWP refrigerants like ammonia. That's going to be a question down the road of what we're going to do at the end of their life. So with that, I want to make sure that
ammonia is interesting. They just bring it back in as fertilizer. That's what happens on ammonia chillers.
Yeah.
Typically, if it's full of water, it got contaminated, it just goes back into that stream, or they bubble it into water. Believe it or not, because ammonia is unique. It's very reactive, right? So it'll transform itself without any help.
Yeah. No. Exactly.
So, yeah.
So I think with that, I want to make sure that we give time. I mean, we have 10 minutes left. If anyone has a question, you can turn on your camera or like just simply unmute yourself and ask your questions. I think it was really good that we were getting questions as we were talking, but if I know like a couple of people like David saying, did you have a question? Or like any other one? If you have a question, please unmute yourself and ask your question.
I've got a ton of questions.
Yeah, I mean,
Yes, I know I somehow got my mic to work again. Steve, thanks for the explanation on 410A and what you might be able to do with it as we phase it out of buildings. What are your all thoughts on like hybrid VRF? I'm seeing that Mitsubishi is putting out a product that is able to cut down, I think, 20-30% of the refrigerant load by doing refrigerant to a controller, and then from there it switches to hydronic, I believe. It seems like there's some cool new technologies hitting the commercial market by the end of the year, and I'm just curious what people are.
Variable water flow systems. They're kind of like mini VRF chillers, right? That's essentially what's going on. Reduces refrigerant charge a lot. I think it's a great idea. VRF's biggest problem is you use a lot of pounds per ton of cooling. But you still have the advantage of moving heat around, right? And recirculating, so you can do all those switching of valves and stuff. I mean, there's an efficiency penalty, right? You have a heat exchanger there. But I think this is the kind of innovation that people get when you're forced into thinking a little differently, right? As you move forward, right? Flammable refrigerants, reduce the charge. I want to reduce my global warming impact. Yeah, the grid gets greener. Can I get the efficiency back by throwing more heat exchanger at it? Probably, maybe not, but maybe you need to get out of the pounds of refrigerant. Yeah, I think it's a really innovative idea. People keep, these type of things drive innovation, right?
Yep.
I don't know, Joe or Brian or Mohammed, comment on that.
I think that technology will be really big, especially when you consider tall buildings in like Chicago. You just can't implement VRF if the building's too tall as it stands. And I obviously, if you're able to combine a hydronic system that can better handle the pressures and distribution in the buildings, it'll improve the ability to adapt the building for an air source heat pump system and get away from fuel source heat.
Great.
Yeah. Yeah. I like water systems. So for on the comfort side, and you get a sort of a wider range of operating temperatures for comfort and efficiencies that way, just for the user experience. But so that kind of combination where you get the good efficiency, but the comfort levels of that, and owners can handle and think about water systems a lot easier than they can, and their maintenance guys can think about that a lot easier than a all VRF system that they have to call in a specialist all the time.
So, water's cheap too, so
especially around here.
Yeah.
So,
yeah, absolutely.
Water's cheap to put inside a tubing.
Yeah.
Yeah.
Versus refrigerant.
If we ever get to a point in Illinois or Chicago where we have a price for carbon, I'm curious to see if this happens in New York, but do do you see maybe a bigger radiant system making a more competitive argument, say on like a high rise or residential? Because VRF is just, it's super efficient, it's cost effective, you know, it knocks it knocks radiant out of the conversation, in my opinion. I think you guys would probably agree with that. I'm just curious, once you start layering in cost for carbon though and refrigerants, and you know, what other hydronic systems might we see too? I'm getting really excited about the opportunities and what might happen in the industry. But I do, you know, VRF's great for now anyways.
Well, and we're seeing a lot of heat recovery coming off chillers. I mean, that technology's been around a while, but it's really hitting the mainstream for chillers to save you on basically electric heating on for either domestic water or if you have simultaneous loading if you need it. And that's really turning the tide back to hydronics as well, especially when you get into carbon taxes. So if you get in, or a carbon charge, and it might just get rolled into the natural gas charge, which would be the way to do it. And that's, in a heating dominated climate, you're going to be running into how do we get somewhere close to the energy, the BTUs per cubic foot or BTUs per kW equivalent of natural gas versus electricity to make it really worthwhile and market adaptable or acceptable.
Yep. Do we have any other question? Or I think we have 4 minutes left. I think now it's the time. I mean, just a final call for if you have any question, or if not, we can have 1 or 2 final thoughts or comments and then wrap up the conversation. I think it was a really good topic. It's, I mean, obviously it's not, I mean, when we are talking about decarbonization, I think the next conversation that we will be hearing more and more is going to be the impact of refrigerants on the reducing on the whole trend of reducing the carbon emission in the building industry. And I'm sure this conversation would hopefully going to produce some good contents for the CLF website next to the other one that the CLF Austin did. But yeah, this is the final call. If you have any question, unmute yourself. If not, we can, if Steve, Joe, Brian, if you have any final thought, we can hear from you and then wrap up the session. No final thoughts, no conclusion. Okay. I mean, it's been a great conversation. I had 2-3 pages of notes. I got most of my answers. I'm happy we covered so many things related to the replacement options, the barriers, the drivers, the codes that gonna come up, the conversation around maintenance, about leakage, about training, about toxicity, about the end life of many of these materials. There have been so many topics and outlines that we covered. And yeah, we are all excited to see this transition in the next 10 years. I think this event was a good event to see who out there is excited about the refrigerants. It's definitely not something that in a glance or in the first impression, people feel that they're excited, but more you dig into that, you get the importance of them in the trend. So I was happy that we've been able to connect. Yeah, and with that, I think we can wrap up the conversation. Juanita and Emily, do you have anything to add? And David?
No, just thanks to the presenters, and look forward to talking to everyone next month.
Cool.
I just want to add, and maybe I kind of came in late to the conversation, but certainly seems like there's lots of changes to ASHRAE. And, you know, I think maybe the future is, you know, more changes to ASHRAE and less focus on things like LEED, more looking to stretch codes, yeah, and and ASHRAE for guidance.
Yeah, ASHRAE actually has a decarbonization task force that they've developed.
Right. I'm
So-
actually on one of these. I'm on ASHRAE 209 task force.
Mhm.
Is about for energy modeling. So that sounds.
Yeah, it's going to be interesting what all comes out of that.
Yep.
When everybody puts their minds together to put something together like that.
Right. Right.
No, I agree. I mean, I think like we used to have one or two drivers for decarbonization, and now it's like the stretch code and ASHRAE are becoming the main drivers
Yep.
to transform. And I think I think that
Right.
could be even a better driver that and
Yep.
could be more kind of inclusive as
Right.
well.
Yeah, and as ASHRAE transforms, that's going to affect our codes.
Yeah,
for sure. Yep.
Absolutely. Okay. Great. Thank you everyone for attending. As we mentioned in the beginning, the recordings of this session will be available on the CLF website, and stay tuned for our next events. We're gonna have another event next month, and our routine is to just try to have a monthly event. So thank you all for attending, and have a good day.